Okay. Is recording now? Hello? Class is recording?
Yes, sir.
Okay. So what we'll do, Bernoulli, he derived the equation, right? So if you apply the Bernoulli equation between 2 points A and B, what is the equation? This will be the equation. What does it mean? That means total energy of summation of 3 energy. That means this P by A, this square by 2G and Z is always constant. That means fluid energy is not reduced, right? So this is not practically right, because if fluid flow through a pipe due to the viscosity of the fluid and also due to the surface friction at the wall of the pipe, there is some energy loss inside the pipe, and it depends on how much the distance between the 2 points. That means if distance L is increased, say 2 mile, 5 mile, your loss will be more. L is decreased, loss will be less. Also, it depends on the what type of fluid flowing. We know we have viscosity of the fluid. If this value is high, there will be higher frictional loss, and also depends on the surface roughness of the pipe and diameter of the pipe, and also what type of flow inside. Okay, so we need to make some correction in the Bernoulli equation. So what is the correction? We are applying some frictional loss on the right side. That means when fluid coming from point A to B, then he lose some energy in the path, in the way. That energy is this much. Plus the energy, actual energy remaining in the fluid at point B is this much. For example, after your class from the campus, you buy some candy for your younger brother or sister. Then on the way, you are going home. But any reason, you have some hole or leak in your bag and you lose 50 candy, drop in the roadside. So this 50 candy will be your loss, frictional loss. What is the remaining candy? You then have 130. So same thing over here. On the way, 50, 100, only 50 amount of fluid energy is lost in due to the frictional loss. And at point B, you have only 30 energy, 130. So total is 180. Okay, that way you can think. Now, we need to figure out this loss. How we can figure out? You see, if we apply Bernoulli equation between 2 points A and B, then this 2 point elevation is same. They are horizontal. If diameter of those pipe is same, then V will be how much? Velocity will be Q by A. Same amount volume of water or liquid is flowing through the pipe. So Q is same. That means V1 equal to Q by A1. Similarly, V2 equal to Q by A2. But these 2 points A and B, if pipe diameter is same, then velocity will be same, right? So these B's will be out. So what are we getting now actually? HLF equal to, we are getting PA by gamma minus P by gamma. That means you are getting this value, this much loss, right? So how we can measure? If we install a pressure gauge right over here, pressure gauge right over here, we measure the pressure. then you will know how much the loss is there. But sometimes distance between two points might be 5 miles, 10 miles. How will get the pressure difference? You have to travel or you have to use some sensor, right? That is feasible to figure out the loss. But you like to design a pipeline. So you are working in a project, say, delivering crude oil from Iran to China. In that case, how will you figure out the loss? So you need to figure out the loss mathematically before you design the pipeline. So, and this frictional loss depends on some body of the fluid, that is called viscosity of the fluid. Then depends on how much the surface finishing of the pipe, that means surface friction. Then what type of flow? Is it a laminar flow or turbulent flow? So three criteria will influence on your frictional loss. Okay. Now, how we can know this frictional loss? We can figure out by three equations. Number one equation is called Hazen-Poisson equation. Second one, Darcy-Weisbach equation. And Darcy-Weisbach equation, he used a constant that is called Darcy friction factor. Now, in the previous slide, you know that it depends on frictional loss, depends on the type of fluid. That means viscosity of the fluid. So viscosity of the fluid, you know, this is the data. You can look to the handbook or property of the fluid, you will build the viscosity. Then type of the flow. It is a turbulent flow or it is a laminar flow. This is one thing. Other thing, it depends on the how much surface finishing in the pipe. That means I'm saying friction at the wall surface. So these three properties depend. Now, how did you know a flow is turbulent or laminar? Normally, if you look through a glass tube, say water flowing through a tube, and it is transparent, that means you can see from outside. So you add some color, then you are able to see the flow is laminar or turbulent. But for example, air flowing through a glass tube, I will figure out the color of the air. You can put some smoke, but it might sometimes not feasible, right? Liquid petroleum crude oil that flowing through a steel pipe, you cannot see from outside. So mathematically, you need to have a formula to know whether flow is turbulent or flow is laminar. So that laminar flow or turbulent flow is determined by another formula that is called Reynolds number. Not formula, another number. So to figure out the Reynolds number, you need to have a formula. What is that formula? Say if I say Reynolds number equal to Rn, this Rn equal to rho Vt divided by viscosity of the fluid. Rho is the density of the fluid. This is the dynamic or absolute viscosity of the fluid. V is the velocity of the fluid inside the pipe, and D is the pipe diameter. So after you figure out a number, from that number you need to decide that flow is turbulent or flow is laminar. For example, you can say if Rn is 1 to 10 or 1 to 15, then you can say flow is laminar. Then you can say if Rn is higher than 25, then it is turbulent. So you need to know what is this range. Is to 1 to 15 or 25 or what else? And how will you figure out the Reynolds number? That I give you the formula. So right now, you just remember we need to know the Reynolds number. Okay. We'll discuss it Reynolds number later on. So it's a flow criteria you need to find by Reynolds number, whether this flow is laminar or turbulent. Then that's the friction factor. That's the he derive a equation. Say, for example, HLA, that means frictional loss, equal to FL B square by 2GD. Say D is the diameter of the pipe, D is the velocity inside the pipe of the velocity of the fluid, L is the length of the pipe, and F is the friction factor. This friction factor depends on what type of material of the pipe. Is it a plastic or is it a glass tube or it is a cast iron? Then depends on diameter of the pipe. What is the diameter? Then depends on how much surface is finishing in the pipe. Okay, even say you have a glass of on the top of your table, you put your hand, you see smooth. But if you look in by microscopic image, you might see the surface is not perfectly smooth. Still, there is some surface roughness. Okay. Similarly, you buy plastic pipe, you put in your hand, you might say there is no surface is smooth, but actually not. Okay. Now, one thing we need to know that how we can apply one modification if there is a pump in the fluid system. There is a turbine in the fluid system. So what pump does? Actually, it adds energy to the fluid. For example, you living in a home, 6-story building, your water tank on the ground, right? In the roof, you have the water tank, rooftop water tank, and through the pipe, your water from the underground tank is going to this tank. How it's going? If I say, okay, take a bucket and fill up the tank, how long take time? Huge time, right? So the water flowing, if I say jumping from ground floor underground tank to the rooftop tank, say height about 70 feet, how is it possible? How do you get the energy? Due to the pump. That means pump add energy to the fluid. Similarly, turbine, what it does? It absorbs energy from the fluid. For example, you have water tank, you add a little wheel over here. In that wheel, you add some blade. Okay. Now you make a pipeline from here, release the water from the tank. The water hit the blade, then this will rotate. That means this is the turbine, right? That means he's using the energy of the fluid. So turbine is the drinker, energy drinker of the fluid. He will take energy from the fluid, produce mechanical energy. But pump, he take the mechanical energy, convert into the fluid energy. So he's taking energy from a motor. That means motor is taking electricity. Then motor rotating the pump impeller. Then he adding energy to the fluid. Okay, that's what you need to remember. Now, if there is a pump at point A, how we can apply Barnard equation between point A and B? That we need to figure out. Okay, so you see, we are talking about the real fluid that Bernoulli's evaluate the Bernoulli's equation. He said there is no viscosity of the fluid. That means he thinks that fluid is ideal. But right now we see fluid has a viscosity, right? So obviously there will be some loss in the pipe that I'm saying HLF. Now, how we can apply the formalization? So fluid just coming at point A, how much energy it will have? It will have this much energy. P A gamma B square by 2G plus Z. Then if coming over here, the pump adds some energy that is called H pump. What is the H pump? Actually, what is the unit of all these part of the equation? P by gamma, what by unit? P by gamma equal to will be a meter, because what is the P? P equal to rho G H. That means coming gamma H. So when you figure out P by gamma, what are you getting? Only H. So the H pump unit is meter, Z also meter. This forward to G, this also meter. That means it's giving head in terms of head of water or head of fluid. So H pump, when you like to buy a pump, go to the store, they have a specification, they mention there, the head is 30 meter, head is 20 meter. So head is more, that means your pump is more powerful. Okay. So if we have a pump head, say 10 meter, how much pressure energy you can create? This maximum pressure energy, you can figure out that P equal to rho G H. This H is the head of the pump. So this much pressure we can generate. Okay. Now our target is, if there is a pump in the system, how we can apply the formalization. So ultimately at point A, you have energy, this much energy is coming with the fluid, then pump is adding some energy with this one. That means energy increase. At point B, fluid is getting out from this point with this much energy. And how much the loss in the pipe? A second. Okay. I can explain it in terms of if it's a candy. Okay, say you have some candy in your, you buy some candy in your, from the store, from the campus. So your candy is 150. When you're coming to in the your school bus, say one of your friend give you 60 candy. So in the bus, before your journey, totally you have 210 candy, right? Now you're sitting by your another friend, and he's stealing your candy one by one on the way. Say he's stealing 80 candy. So at the point B, you're coming in the home. How much candy you will have? So 130. So this 80 candy, your frictional head loss. And this one energy is the remaining energy. And 150 is the energy of the fluid before at point A. And at point A, pump is adding energy 60. Okay. This way you can think, so it will be easier to apply and understand. Okay. Second situation, if you have the turbine in the pump, then what will happen? So left side remain the same as I explained it in the previous slide. And at point B, fluid is coming out with how much energy? This much energy. Then some energy lost in the road, they say left. And turbine, it brings some energy to produce mechanical energy. Say is this much. Then turbine, it don't have energy 100% efficiency. Say if he absorbs head of water 100 meter, then he cannot produce mechanical energy by same amount, then efficiency will be 100%, right? So say your is efficiency 90%. So remaining 10% energy will be your loss. That is called mechanical loss. Now, you can think other way that I explained it in terms of candy, that you have 130 candy, you coming to the gate or bus, say gate of the campus, one of your friend give you 50. So you heading to your home with 180 candy. So this right over here is 180. Ace pump will be 50 and this 3 will be 130. Now you are on the way, some of your friends stealing 20 candy from your bag. So that will be your ACLF. Now, turbine, I'm telling you, he is an energy drinker. So at point B, that when you came in your home, you came in your home or you stop by another friend, he say taking 60 candy. So how much candy you're remaining now? 100, right? So this 20 and this 60, 80 minus 180 minus 80. So you have 100 candy in your bag. Now, say you turbine, you think as one of your friends. He takes 60 candy, but he's not able to eat 60 candy. He eat 50 candy. So what will be the wasted amount? 10. 10 will be your loss. So you can say 100 plus loss 20, fictional loss right over here. Then turbine take 50 and mechanical loss is 10. Okay, this way you can think. Now, what is the formula to figure out the efficiency of the turbine or efficiency of the pump? You will learn it in your fluid machinery class. But so right now we'll just give you the equation. So fluid power of a pump or turbine, you can figure out by this formula. H rho G. H is the head of the pump or head of the turbine. Then you multiply by the Q. You will get the power of turbine or power of pump. Now, how you can figure out the efficiency of the pump? So pump, what is the efficiency? Power output by power input. So efficiency of the pump, this will be in the bottom will be P in. So he's taking from P in from where? Input power from the motor, first power of the motor. Right? And how much energy is adding to the fluid, that will be output. So the energy is rho GH, that means H pump into Q. But in case of turbine, it's opposite because he's taking energy from the fluid. So input energy will be fluid energy. So in that case, rho GHQ will be the bottom because this will be P input. That he's taking fluid energy. And what will be P output? That will be mechanical energy, right? So this one will be actual output. So P out divided by P in. So you need to remember these two formulas. Any questions from this slide? Anyone?
No, sir.
No? Okay. So we'll stop this lecture sheet 8. Let's start with lecture sheet 9. Okay. Nine. Hello,
Yes, sir, we can see.
Hamda.
Yes, sir, we can see.
You can see. Okay. Good. And I put over here some questions that on the previous lecture sheet. So you can go through all the questions and figure out the answer. All the answers remain in the your lecture sheet. Okay. This is the assignment. Normally, I give some time, but in your case, assignment I'll give you later on. And this problem already discussed. So how we can solve it. Now, what is our target? To how we can figure out the frictional head loss in the pipe. So you can apply the Bernoulli's equation correctly. Now, Hazen-Poiseuille in the previous lecture sheet, we talked about three equations. Hazen-Poiseuille equation, Darcy-Weisbach equation. And also we talk about Taylor's number. So Hazen-Poiseuille, he derived a equation. He's saying that amount of fluid flow through a pipe will define this formula, like Q equal to delta P. That means delta P is the pressure difference between these 2 points A and B. D to the power 4 is the diameter of the pipe, 128 meter L. L is the length of the pipe. We can normally, there is a derivation, but I already told you at the beginning that our class is actually 6 credit. 2 course we compact in our course. So normally we can get that first time because we have to finish officially by this week, your mice part, right? So I just give you the equation and describing all parameter. But if you interested, I have the derivation I can give you, or you can derive, look some book, and if you have question, let me know. Okay. So Hazen-Poiseuille equation, Q equal to delta P pi d to the power 4, this one. So what is the delta P? Delta P equal to PA minus PB. That means pressure difference, right? So this pressure difference, you can easily figure out from the equation. You can say delta P equal to Q into 128 mu divided by pi d4, right? But there is a problem because his equation say right after all the parameters. Q is the discharge meter cube per second. P is the pressure difference between 2 points. Mu is the viscosity of the pipe or absolute viscosity, and L is the length of the pipe. But problem is that his equation only valid for laminar flow. If flow is incompressible and Newtonian fluid. So if there is a turbulent flow, then you cannot apply this equation. Okay, but if it is flow laminar, then you can use. Then you need to know that you need to use a Reynolds number to figure out if your flow is laminar or turbulent. So due to this limitation, Darcy-Weisbach, he developed another equation, and his equation we can use it in both laminar flow and both turbulent flow. Right over here, I just put the slide from the previous lecture, I think 5 or 6, that what is the definition of laminar and turbulent flow. In the laminar flow, fluid travel in a layer by layer, and there is no pollution of fluid particle or fluid element between two fluid elements. That means there is no transfer of momentum while fluid flowing through a pipe. That is called laminar flow. But in turbulent flow, there is a transfer of momentum because this fluid element right over here, next moment he might hit these two together. So there is a continuous transfer of momentum between the fluid element. So this is the turbulent flow. Now, This, as far if you add some color in the fluid, you can see. But you might have opportunity to add the color in the lab or experiment, but out of the real situation, you cannot apply the color. So we need a mathematical formula. So this is Darcy-Weiss equation. That HLF is saying frictional loss between two portions of pipe or two distance is between point A and B is HLF equal to FL V square, V average square to GT. Now, what is the V average actually? V average is equal to QA. We know that you figure out the velocity by QA. But why we are calling it average? For example, if there is a flow inside a pipe, then we think that all the full particle is traveling with same speed. That's why we just figure out V equal to QA. But in reality, what will be happen that fluid particle right over here, say I'm taking some fluid particle right over here. So you see fluid particle at the wall, he will not able to move. To the viscosity, he will stick with the wall. But next fluid element, say this one, he will travel a little bit faster. And at the middle one, he can travel more. So similarly, things happen in the other side. So fluid velocity profile, if you draw, it will be like that. That's not the thing. At the middle has higher velocity, at the mid center line of the pipe. If from the center line you move gradually, velocity is decreased. So we are figuring out QIA, that is not the actual velocity. That is giving you the average velocity. Okay, that's why we say V average equal to QIA. So this is Darcy-Weisberg equation. You see the L is the distance between 2 points. Why do you like to figure out the head loss or length of the pipe? V average velocity of the fluid inside the pipe equal to QIA. L length of the pipe unit meter, and this D is the diameter of the pipe. Now what is left? F. F is called Darcy friction factor, and it depends on laminar flow, turbulent flow, and also it depends on surface roughness and the material. Okay, so we need to know how we can figure out the Darcy friction factor. Okay. Now this is the Darcy equation. Okay, and he figured out that if flow is laminar, in that case, the value of constant F will be 64 by Reynolds number. So how to say? You need to know the Reynolds number. How will you figure out? If flow is turbulent, then you need to use this big equation. So you see this, in case of turbulent, you have a big formula. If its flow is laminar, you have a very short formula over here, right? So in this bigger one, you see how we'll figure out. This E, epsilon, this epsilon is called surface roughness. How we'll figure out? In our Bangladesh, you need a pump or to buy pipe, you just buy it from the store, right? But if you need to buy pipeline for the industry, say for chemical industry, for a power plant, then you need to contact some manufacturing company, and you might look their website, and they have a different specification of the pipe, and they put their surface roughness in the specification. So this epsilon is the surface roughness and D is the diameter of the pipe. So this is one ratio you will get from the data of the pipe. You get this one, right? Reynolds number you need to figure out. Now this constant you see the both sides, the left side and right side, and this is locked in. How we can solve it? Still, yeah, if you use scientific calculator, you can solve this equation. I figure out the value of F from there. If you know this value, E by D, when you know the Reynolds number. Okay. So two things over here. You need to know flow either laminar or turbulent. If it's laminar, you use this one. Turbulent, if you use this equation. Now, how you figure out by Reynolds number? So you need to know how you can figure out the Reynolds number. And this equation you see, it has a how many variable it has. You see three variables. One is Reynolds number, other one is this ratio of surface roughness by diameter of the pipe, and third variable is the friction factor. So Darcy Weisbach for the did, he plot this equation in a graph that is called Moody diagram. So to figure out the F, you can figure out these two equations, or you can use the Moody chart. By sometimes it's called Moody diagram or chart. From Moody diagram, you can figure out the work for both laminar and turbulent flow below of friction factor. So how it is look like, we'll discuss this later on, but I just giving you some preliminary idea. It has a three axis. Along horizontal axis, it has Reynolds number R. Say along vertical axis. Okay, could you hold on one? Hello. Okay. So in the horizontal axis, you have Reynolds number, and in upward direction on the right side, you have the ratio epsilon by D, and left side you have friction factor, and your graph will look like this one. So at first you figure out the Reynolds number, say is right over here. Then you figure out ratio epsilon by D. So it's coming over here. Now you make a line. You are coming over here. So this will be your friction factor. Okay. So say you are right over here. You are right over here. So you travel inside the graph. Then if you list number right over here, you're hitting this point. Then coming left side. We'll show you in detail that how you can use the Moody diagram to figure out the friction factor. So right now, I just give you a preliminary idea that how we can use the Moody diagram instead of using this big equation. Now, you need to know that how we can figure out the Reynolds number. This is the definition of laminar flow. We don't need it. Okay. So how you can figure out the Reynolds number? This is the formula of the Reynolds number. We already talked about a little bit, right? That rho VD. Instead of D, right, but they push DH. I'll explain it why. So this is formula. Actually, how it is coming, this formula. The Reynolds number, it's a ratio of viscous inertia force, it's right, inertial force to the viscous force of the fluid. That is called Reynolds number. So what is the inertia force coming from the Newton's second law, F equal to ma? That is the inertia force. And viscous force, you know the Newton law of viscosity, tau equal to mu dv by dy, right? So this tau, if you multiply by area, tau into area, then you will get the viscous force. Okay. Now this equation I can also write down tau big u by or y, v by y, right? So this ratio, inertia force by viscous force. So I can say inertia force equal to tau into area. I'm sorry, viscous force, and inertia force Newton's second law, F equal to m. So now, how we figure out the mass of the fluid, m? If you know the volume multiplied by rho, you get the mass, right? So what is the unit of how you get the rho volume? Your volume you'll get, if the dimension is L, unit of volume is L cube, right? For example, you have a cube, then volume will be L cube. So I put the volume L cube and this is the rho. So m equal to v into rho. What is the acceleration? Velocity respect to time, change of velocity, right? So I can say v by t equal to acceleration. And what is the tau? Tau equal to this formula. Tau equal to mu dv by dy, or we can say mu big V divided by y. So we put y mean distance between the upper plate and lower plate, law of viscosity. So mu over here, so we can say V instead of y, we just put L. And what is the area, unit of area? Meter square, feet square. So we can put L square. Okay. Now we just simplify the top and bottom. So in the bottom, this L square will be out, there will be only one L. So mu B L. And in the top, you see rho L square. If I simplify this one, I'm keeping rho L square and I'm keeping B separately. And one L over here, this L, I am keeping in the L by T format. Okay. So what is L by T? L by T equal to T. So this B, V square. So at the top coming rho L square, V square. Then you simplify, there one L will be out, one V will be out. So this one you are getting Reynolds number, rho V L by mu. Now, rho VL is seems like the length, right? So instead of length, we like to put rho V D by mu. Because if we have internal flow, normally we use a circular pipe or we use a duct, right? Like in all commercial building, they make the air conditioning unit, they use the duct, right? So rho VD by mu. Now, what is this D? I will figure out. If instead of a circular, you have a rectangular pipe, no circular, I will figure out the Reynolds number. If you have a triangular shape pipe, then I will figure out the Reynolds number. Rho V L by mu, this equation normally is used when you have a flow over a flat plate. Say flow is going over flat plate. You thinking right over here, your L will be this much. You like to figure out the first number right over here, you need this much length. But what about inside a pipe or inside a flow inside a triangular tube or rectangular tube? Sometimes you might have a hexagonal tube, like this type of hexagonal tube. Then what will do? So instead of D, rho VD, we'll say Reynolds number RE equal to rho V, we'll say DH. DH by mu. Why is that DH by mu? This DH is called hydraulic diameter. So DH is known as hydraulic diameter. So what is the actually hydraulic diameter? Why we are using this one? Because sometimes you have a circular pipe, but it is not full, say flowing only this much. In that case, whose diameter will use? If you use the full diameter, you are not getting the real number because the flow is half. If it is full, half, full, then you can use the D. So that's why they use one more term is called hydraulic diameter. So what is hydraulic diameter? Equal to 4 into cross-sectional area divided by weighted perimeter. Weighted perimeter means in Bangla, beza ongsho. Say you have circular pipe. So at the top, 4 into area. So what is the area? 4 into pi by 4 into d square, right? This is area, 4 into area. So 4 out. So at top, you have pi d square, right? Then weighted perimeter. Weighted perimeter means if this pipe is full, then this much length will get weighted. What is the length? Pi d, 2 pi r or pi d. So I'm saying only pi d. So resultant you are getting directly d. So in case it's half flow, then weighted length will be from here to here, the length of this half circle, only pi r. Okay. So just remember this formula, hydraulic diameter equal to 4 into cross-sectional area divided by weighted perimeter. Now, how will we figure out hydraulic diameter for a square duct or for a rectangular duct? So definition, 4 into cross-sectional area divided by weighted perimeter. So look in the rectangular duct. In the rectangular duct, what is the area? A into B. So at top, 4 into A. What is the weighted perimeter? That means we count the length of the perimeter. So length of the perimeter would be, this is A, this is also A, this one also B. So 2A plus 2, this is the weighted parameter. After simplify, we get this one. Hydraulic diameter for a rectangular pipe or duct. That means you are getting equivalent radius of the rectangular duct. If you have a square duct, then 4 into a square, area is a square. What is the length? For length is same, so 4A. So finally you are getting only A. Similarly, for circular tube, you are getting only, or pipe, it is only D, is the hydraulic diameter. Now, after you got hydraulic diameter, then you need to figure out the Reynolds number. How you get Reynolds number? You put over here. So rho is the diameter of I'm sorry, density of the fluid, and V is the velocity inside the tube or pipe. I will get the velocity V equal to QIA. Hydraulic diameter, you need to figure out as I showed the previous slide. 4 into cross-sectional area divided by weighted parameter. And if it is a circular pipe, then you can immediately put hydraulic diameter equal to diameter of the pipe. But it is a rectangular or other form, then you need to figure out the hydraulic diameter. Viscosity, property of the fluid. So you see everything is known, only you need to figure out the hydraulic diameter. So you have Reynolds number, then that Reynolds number you need to compare with this data right over here. You need to figure out that whether flow is laminar or flow is turbulent. If flow is less than Reynolds number less than 2300, your flow will be laminar. If flow is between 2300 to 4000, then it's called transitional. That flow becoming converting from laminar to turbulent. And flow is higher than 4000, that is becoming turbulent flow. Okay. So flow becoming from laminar to turbulent, it takes some time. It doesn't happen immediately. So that's why there is a transition period. For example, if you are burning a mosquito coil, then you might see your coil is burning right over here, smoke coming out certain distance linearly. Then this smoke gets mixing up. Okay. So this much portion of flow is called laminar flow. And some portion is called transition, and this amount is called turbulent flow. And if you are able to see clearly somebody is smoking, you see smoke coming out clearly this portion, and some portions still going the straight line, but all the smoke kind of rotating. Then you'll see they are rotating more and spreading to the both upward and downward direction. So this portion is called transition from laminar to turbulent, and this portion is laminar flow. So we are not worried about the transition flow. We are worried that whether flow is laminar or turbulent. If you have Reynolds number in between this region, you can say flow is over 2300. You can say turbulent. Okay, if less than 23, you can say laminar. But when you solve the problem, but when you go for job interview, they might ask what is the Reynolds number, what is the application of it. Application of it to figure out the flow turbulent or laminar. Then say how now flow is laminar or turbulent. Then you describe that if less than 2300, flow laminar, is higher than 4000, flow is turbulent. Okay. Okay. This slide, the same thing I explained before, that if you have a pump in the fluid system, what does it mean? So fluid, analysis of fluid at point A, entering just entering at point A with this much analysis. Then for the ACE pump,